All right, folks, we're back at it. We're going to be looking at error detection and parity, which is the next section. Sorry, I'm all out of magic tricks, so we're not going to work on that right now. But what happens now when we have a scenario that you are going to a bank and you withdraw some money or even deposit some money? And you might have heard stories in the past where somebody goes to an ATM and they withdraw money, and then when the money is withdrawn, instead of withdrawing, say, $10 or $20 from the ATM, all of a sudden it spits out maybe like $3,000. All right, and then the individual might think, oh, well, it was their mistake, so I'm not going to say anything. Well, how do errors like that actually occur? And they do happen very seldomly now, but they still happen. But it's much, much harder because there's so many checks and balances in place now that something like that is a rarity. All right, but when it comes to that bit of information, when we deduct money from an ATM, all right, everything is broken down at its core level into binary code. And then the binary code, the string of ones and zeros, is then transmitted and transferred. And then when it's received on the bank's computers, it's basically saying, oh, individual wants to withdraw $20 from his account or her account. So let me go and verify that they have enough funds in their account. And if they do, it sends a binary message back saying, okay, withdraw the $20 as requested. Well, as you know, when we look at binary code, it's not allowing me to draw on this. That's terrible. Anyway, let me flip over to my notebook here. If I were, again, to use binary code, okay, using my byte over here, my 8 bits of data. Okay, remember what we said, that we have the values of these places within my binary code: 1, 2, 4, 8, 16, 32, 64, and 128. All right, if I wanted to make the number 20, well, then what I would do is I would flip the number 16, and I would flip the number 4, and I would get a string of code that would look like 000-10100. Well, what happened now in the process of sending this information if this digit over here was flipped, so that an error occurred and we now have information that looks something like this? Well, rather than the value, as we know, as we just went through, this is the value 20, but this now is the value 128. And so when I would add the two together, we would get a total of 148. So if there was an error that occurred with just in this one string of numbers, and that digit got flipped, we would end up with $148 spitting out of our machine, rather than just a $20 bill, which is what we were looking for. All right, so how does those errors occur, or how can we prevent those errors? And, moving forward, what would we do to make sure that it never happens? Because one digit can make a monster scenario. Again, another example over here. Now, if we were to expand it out, not just to the 8-bit number system, but if we were to expand it out even from a 16-bit perspective, all right, so 2 strings of 8 bits of data. As you can see in this first digit, we have all zeros, but a 1 all the way at the bottom here. And that would obviously be equivalent to the value 1, so therefore that would represent or resemble $1. But if we took the leftmost digit and we flipped that, all right, and if we counted all 16 spaces by the doubling process, that first digit that is flipped would hold a value of 32,768. So if there was an error and that one digit flipped, and you went to the bank to withdraw $1 or to deposit $1, and all of a sudden you get your printout, and the printout shows 32,769, that's because of the fact that there was an error, then that digit flipped from a 0 and 1. All right, and so that's obviously an extreme case, but one that kind of makes sense, because when everything is working off of binary code, if you have your any bit that is flipped incorrectly, all right, you're now dealing with different information than what you normally had. All right, so this is where the parity bit comes into play, because a parity bit is used for error detection. And what it means is that there's extra bits of data and information, and I'll show you what it looks like in an upcoming slide. There's extra bits of data that are presented or that are injected in between your data, and the purpose of the parity bit is to prevent any sort of data bit from flipping. Right, and in parity, we can have two types, two processes. We can have an even parity, or we can have an odd parity. All right, and depending on what we mean by even or odd, depends on how, the number of ones or well, not ones or zeros, but the number of ones that we have. Do we have an even number of ones, or do we have an odd number of ones? All right, so in an even sequence, the number of ones add up to be an even number. And then in an odd sequence, the number of ones add up, obviously, to an odd amount. So what does this look like from a binary code standpoint? So as you can see with the first set of numbers, we've got 3 zeros plus an additional 4 zeros. And I'm looking at the first column on the left-hand side over here. We have all zeros with no ones. So in order to keep the parity even, okay, we have to add an extra 0, which is the red 0 at the end. That's your parity bit. And because 0 counts as an even value within computer programming, or within this binary code example. So if we go to the next example, down the second set of numbers down, we have 0, 1, 1, 0, 0, 1, 0. So we count the number of ones, and we have an odd number. We have three individual number ones. So we would have to then add a 1 at the end, because again, we're trying to make an even parity, and therefore we have to have an even number of ones. The next case, we have an even number of ones. Okay, we got 4 total, okay, which means we have to add a 0 at the end in order to maintain that value. So, and that will go on and on and on. So if we look at the right-hand side, okay, this is, we're looking at odd parity. So that means that we have to have an odd number of ones. And it's the exact opposite of what we see in that middle column. We see that in the case where we had all zeros, we're going to add now a 1 in front of that. And the reason being is because we want to make sure that since we're dealing with odd parity, we have to have a total of ones that are odd. So how does this work? All right. So the gentleman that created this, the process of parity, is a gentleman by the name of Richard Hamming. All right. And as you can see on the diagram in front of you, parity is broken down just like in that in the diagram. So what you see are P1, P2, P3, and then we have D1, D2, D3, and D4. P stands for the parity bit, and the D stands for the data bit. All right, so I'm going to kind of give you a little bit of a scenario to kind of try to make sense of the explanation of how this is. So just imagine two people, we'll call Alice and Bob, have figured out an amazing trick, and they're going to be exchanging their messages by plucking a wire of a guitar string, either hard or soft, to transmit zeros versus ones, right? But because of the fact that they're outside and gusts of wind come by, all right, what will happen is it will cause the string to vibrate, and therefore we'll end up getting false zeros or false ones that are transmitted through the code. Or maybe you can't even discern between them at all. All right, and that will then result in transmission errors, resulting in overall errors within the messages and the data bits that they're receiving. Right, so though they figured out a way to communicate this error-free, even in the presence of noise. All right, so how can they go about doing this? All right, so back in the 1940s, Richard Hamming faced a very similar problem. So he was working at Bell Laboratories at the time, and at Bell Labs, he was basically he was saying that 10% of all the work being done at that time were being done experimenting or modeling on computers, while about 90% of all the work and all the research being done was being conducted in person. Okay, but he did say that he expected that in time that the world would basically do a flip, that 90% of all work and modeling and everything will be done on computers, and only 10% will be done in the laboratory. And I mean, I would probably say he's pretty close to that. And the reason being is because, speed, cost, and effort favor the computer, because the computer can constantly calculate and constantly work and never fatigue. So at this time, computers were used to storing information on punch cards, all right? And they would represent the ones and the zeros by either a hole punched in the card or no hole being punched. And the problem with this is that the system was very prone to errors. And because ultimately it was very common for these punch cards to run through the machines and to either get bent or to be mispunched, or so on and so forth. All right, so holes could be missed, or where holes should have been, no holes were not there, and therefore weren't counted. All right, so holes can get accidentally punctured, causing bits of data to flip from a 0 to a 1 or to a 1 to a 0. And then once those data bits were corrupted, this would then throw a monkey wrench in the system. It would cause errors all over the place, and then the whole system would come to a screeching halt. And what the individuals would need to do is that they would have to go through every single punch card, and they would have to count everything manually, and they would have to see exactly where the error was. And then they would have to manually fix it, and then the system will be able to resume and start running once again. Very tedious process, when you look at it. So what Hamming did, he took it upon himself to devise a method which could automatically detect and correct single-bit errors without interrupting any calculations in his data. So his solution, So his solution basically was rooted in the intuitive idea of repetition, something that we basically do when we're faced with any sort of interference or chance to the part of our message that is corrupted. All right, so his error-correcting codes were built on the simple concept of the parity bit. All right, so the parity bit, like I said, is that single bit which is added to the end of a message, or in front, depending on the situation, to indicate whether the number of ones in the message is the odd parity or the even parity. So if a single error occurs, the receiver can then detect it because the parities will not match. All right, so if the user is expecting an even parity and an odd show up, they'll know exactly where the error, that there's an error in that sequence, and then they can go through and then they could check for the error and then correct it if need be. All right, so, but what he did was, one bit was not enough, and that's kind of what you're seeing on the screen over here, all right, because we have the Venn diagram, and we have the red, the green, the blue, which are the 3 parity bits, right? So he added bits to each block of 4 data bits, all right? So we have the 4 data bits, which are the overlapping blue-green, the blue-red, the red-green, and then the very exact center. Those 4 data bits are your data. The bits on the end, the 1, the 0, and the 0, are your parity bits, and those are used for error checking. So first we start with the 3 parity bits, which can be represented in the circle, and then now the circles intersect, producing the 4 regions, and that's where you have your data. All right. So to calculate the parity bits, what we do, we look at each circle one at a time. So each containing 3 data bits. So we determine the parity bit as before. We add up the data bits and we get either a 0 or 2. Right? So the parity bit is 0 for even, and if we get 1 or 3, the parity is 1 for odd. And we do this for all the circles one at a time. And we end up basically with our 3 parity bits to match our 4 data bits. So these are then placed in a standard sequence as follows. All right, and there's your sequence. When we unravel the parity, all right, we get basically the parity 1 bit comes first, followed by the data 1 bit, followed by the parity 2 bit, the data 2 bit, parity 3 bit, data 3 bit, data 4 bit. All right, and that's how we go from that Venn diagram to the actual what the binary code looks like. So realize now that the system can automatically correct single errors with a simple rule. If a single character occurs, 2 or more of the parity bits will be incorrect. And whether they intersect, where they intersect, is the location of the error. All right, so that's what we're kind of seeing in this scenario here. So in the overlap of the blue and green, initially we had a 0. So what happens now if there's an error and that data bit gets flipped, all right, and it's now a 1. All right, so if a single character error occurs, 2 or more of the parity bits will be incorrect. Like I said, where they intersect is the location of the error. This intersecting data bit is then flipped automatically so that all parity bits are once again valid. All right, so the blue and the red, they look at the data bit that's inside, or the system, I should say, looks at and says, wait a minute, that's supposed to be an even parity. Currently, right now, it's odd, so there's an error there. I must flip that bit in order to make it correct again. All right, and so basically, going back to our Alice and Bob example, this is basically their trick. The additional parity bits are known as redundant bits because they don't carry any new information. And all correction codes work this way. They all increase the size of the source messages, so slightly at the expense of automatically correcting errors. All right, so there is obviously some downside, but the fact that you can actually correct all your errors, in my opinion, is a very good thing, because then you can pass data and messages through error-free, or next to error-free. Nothing's ever error-free. So we also use error correction codes for storage. So for example, on your physical CDs, the information is encoded using special codes so that whenever there's like a major scratch that runs across like a DVD or a Blu-ray disc or anything like that, or dust or anything, it can corrupt long sequences of zeros and ones stored on the surface. So these special blocks of code that we have encoded within our data on our disk, all right, can account for those the error detection for those bits of data that have now been damaged and can overcompensate. That's why if you throw like a DVD, unless it's really severely damaged, if you throw a Blu-ray disc into your DVD player and you play it, even with a scratch on it, it usually can still play the information and with zero, little to no skipping whatsoever, because there's a lot of correction code that's in there that will prevent that data from being misread. All right, so that's basically how what parity is and how it works within a computer system, and why it's important to have, because you want to make sure that your data is always being corrected along the way, because then you run back into an issue where you have the bank, the ATM example, where you withdraw, or even a worse case, I mean, that's a bank error in your favor if you withdraw $1 and you get $32,000. But what happens if you deposit $32,000 in your bank and only $1 gets deposited? All right, you kind of want the rest of your money. So error detection, parity bits, important concept in computers. That's all we're going to cover with that, though. There's more to it than that, but we're not going to go too deep into it, because that you'll do that at upper level computer science courses if you ever take. But anyway, so we'll cap it there. Assignments wise, make sure if you do Friday, make sure that you are working on your program, your enhancement program for your paint pot program, or the paint program that we're doing. So kind of losing my train of thought here. So make sure that you're working on that and make sure that it's submitted by Friday. I have that assignment officially through Blackboard. Moving forward, I'm going to try to have all the assignments go through Blackboard, so you don't have to worry about emailing me. You can just post it right and attach it right through Blackboard. So anyway, I'm going to cap it there. Have a great night, folks. We will catch you with another video on Thursday. Take care.